Welcome, my dear student, to this new session. In the last session, we discussed about the LUV spaces, means sum of a collection of all linear transformations, and then we show that the sum of two linear maps is a linear map, and the scalar multiplication of a linear map is again a linear map. In this class, we start with the composition of a two map, means we take a two linear transformations. Suppose we have a S and T are the two different we have to just in the previous we take both the map in the same, so we have to take it from T from we have a U to V, and we have to take a S from V to W be a two linear maps. Then we can define the linear map TS, or we have to define the ST, and that is called is the composition of these two maps. We can say that suppose U to V we have a map is equal to T, then we have a V to W is the map we have a S, then we can say that this is the our new map, this is called is the ST, as composition T is there. So this means we can say that the composition of two linear maps is the same as when the codomain of the first is the same as the domain of the second map is there. This is defined only in this case. So let us start with the definition. Let T from V to W and S from W to U be a linear transformation with U, V are the vector spaces. So I just take a V to W. So just take I write in the form of a V to W, and this is we have a map is a T, and then we have to take a W to U. This is a map we have to call is a S. Then we have to define a new map. This is called S composition T. This is the map from this is map S composition T is a map from. So this means you can say that S composition T is a map from V to U. So this map is called as a composition map. So like this we can say that into this form V to W and W to S, and then this is a S composition T is a map from V to U. So define a composition of S and T and denoted by S composition T, or more simply we have to just into this S composition T, and then we have to most commonly we use as a ST. So whenever ST means we have to just say that S composition T. So we have to define it by this. We have S composition T. So this means S composition T over the V, some vector V, because V is the element of a V. So for any V belongs to the V, S of T we have to just say that into this form. This can be written as S times we have a T of V, and now that the T of V is the element of a here is the element of a T of V is the element of a T of V is the element of a W, and V is the element of a V. Then we can say that this is the map of this S of T of V, S of T of V, this element of a this U is there. So this means we can say that this in the form into this form we can write in this for all V belongs to the V. So as composition T of two linear maps, we transformation map we have to define into this form. This is called as a composition of this. For example, how we calculate the composition of this, we have to suppose T of we have to X, Y, we take two linear maps. For example, I take a linear map in the form T from R2 to R2, and S also from R2 to R2. We have to take a more simpler. T of XY is equal to we have a X plus Y and 0, and then we have a S of X plus Y is equal to you have a define as a you have to Y and X, and then we have to calculate what is our T of S, T composition S. So T composition S nothing but over the X and Y. We can write T times of a S of X and Y. T times of S and Y is equal to this. So T times of X and Y is the form of a Y of X, and this is nothing. T of define is the form of a sum of these two. So this can be written as a Y plus X comma 0. This is we have to define as a T composition S. Now as composition T we have to just take a X and Y is the representing the T of X S of a T of X Y, and this is nothing but is X in the form of a this is X plus Y comma 0, and this is nothing but is equal to we can say that this is the Y, so Y is equal to 0, and then X is equal to X plus Y. So clearly we can say that S plus S composition T is 0 x plus y, and S composition T of xy is equal to y plus x comma 0 is there. Okay, so now we have to just try to show that this composition is a is linear map. So we have to just say that T and these are the two linear transformation. Then we have to show that the composition is V crom U2 is also a linear map. So take any arbitrary vectors. So we have to show that the linear. So we take a V1 and V2 are the element of a V, and alpha is any element of the scalar. So scalar field is R. Then we can say that write in the S composition T of V1 plus V2. It can be written in the form by the definition of S composition T. This can be S of T of V1 plus V2. And now we know that this T is a linear. So this means this can be written S of T of V1 plus T of V2 by the linearity of the T. And now again because S is also the linear, so S is also linear, this can be written S times of a T of V1 plus S times of a, we have a T of V2. And again use the definition of this composition map. So S composition T over V1 plus S composition T over V2. So this means we have to show that S composition T of V1 V2 is the same as a S composition T V1 plus S composition T V2. So this is first condition of additive of the additive vector addition is satisfied. So now we have to try to scalar multiplication. So that means for proving this, so we have to just try to, this is we have to done. Now we have to try to solve the second one. Alpha is equal to this. So we take a S composition T over alpha times V. By the definition of a composition function, we can say that S of alpha times of a V. And now because this S and T is a linear, then can written alpha times T of V by T is a linear. And now again S is also linear, so this can be alpha times, you can say that you have a S and you have a T of V. And then we can say that simply this can be again alpha times using the composition map. We can say that S composition T over V. So S composition T alpha V is the same as alpha times S composition T over V. So this means both the conditions of a linearity is satisfied. And if both the condition of a linearity is satisfied, then we can say that S composition T is also linear map. So if we have a S and T are two linear maps, then we can say that S composition T is again is a linear map. Okay, so this means we have to the composition of a two linear transformation is again is a linear transformation. Okay, now when this S composition T is defined, and as wideness, this means you can see we have to just take a S composition T is defined from, suppose we have a V to W, and this is W to U, this is S, this is T, then you have this ST. Now we have ST may not be defined unless the range of a T is W equals the domain of a S, then the domain of a S. So this W is the, we can say that this is the nothing but equal to range of T, and this is the also the domain of S. So this S composition T is only defined in the case when the range of a T and domain of a S are the same. Similarly, we can define, we have a, suppose we have a take another linear map from V to W. If we have a S and W to we just change this like this. We take a, suppose we have a W to U, we have a S, and then we have a T is U to V, then this is map is we have a TS, then TS is only defined if this is nothing but is equal to, this is the range of S and domain of a T. So this means as composition S T may not be defined unless range of a T equals to the domain of T. Means we can say that a composition of a 2 map is defined only in the case ST, the range of a T and the domain of A is the same, and then TS is the range of a S and the domain of a T is the same. Okay. Now ST is not automatically meaning that okay, sorry. Now second is this ST is not automatically meaning for even TS is defined. So this is not necessary. If ST is defined, then we can say that T is also defined. So we have only one of them is defined, maybe other is not defined. Even both is defined and then maybe not equal to. In general, we can say that suppose we have to just take a suppose U to W and W to V. We have a, this is S, this is equal to T, this is equal to T of S. But you know that V to W and this is T and this is you have a U to W. This is you have a S. This means this is we can say that S and T cannot be defined. So we have in this case because we should say that this is S from U to W and then T is equal to you have a W to V. Then this S TS is defined because of these two, but ST is not defined because these two are the different. So this means these range of this in the codomains are not equal. So TS is not automatically means T is defined, but ST is not defined here. And in similar fashion, we can say that if ST and TS is both defined and maybe not equal to in general, then ST is S composition T is not necessarily equal to the T composition. As for example, hence the commutative law of multiplication does not hold for a linear transformation. For example, we take a x plus y, we take a T from R2 to R2 and S is also we take a R2 to R2 and Tx we define into this form, and as this is clearly both the map is a linear. Now we have to calculate what is our ST as composition T over x and y. This can be written as a S of T of xy, and S times T of xy is nothing but equal to we have x plus y and y. Now S can be defined in the form of a x plus y comma 0 first term as it is, and this is you have a S composition T into defined in this form. Now similarly we calculate what is we have a T of S xy. We can say that T of, by the definition of a composition map, xy. Now T of x and y is equal to you have a x comma 0, and now we have a just that by this second property T of xy defined as the x plus y comma y. So y is equal to 0 term, so you have just the x plus 0 comma 0 is equal to you have a x comma 0. Now for all x and y you can see this T of xy is equal to the form of x plus y comma 0, and this Ts of x is equal to this. Clearly we can say that ST is defined and Ts is also defined, but ST is not equal to TS. So in general we can say that the commutative law of a multiplication and the composition of a linear map need not be true in general. Okay, so now we have to just say that what about the R, S and T associativity conditions of a composition of a map. For example, we take a map, we take a defined as a T from, we have to take a U to V, then we have a S, we take a from V to W, and we have to take R from W to we have a Z. So now we take a first define into this form. So we have a map is from U to V, we have to define as a T, and then V to W we have a define as a S. Then this map is nothing but is equal to we have a ST. The ST is nothing but is equal to you have a W to V to U to W, and then we can simply say that this is U map is equal to you have to just say that ST, and now we can define a W to Z, and now we have a W to Z. This is a map we have a R, and now this is Z2 we can define is a R over S of a T. So R over S over S of a T, so we can just say that R over S of a T is a map from Z to U. And now we check what is about the over RS over T. So RS over T, we have we just take we have a V to W, we have a S, then we have a R, we have a W to Z, and this is map from Z to V is you have a RS. So we just say that this is the map of you have a R of S. Now we just say that, so this is R over S. Now we just say that this is nothing but is equal to, we can say that, and then we have a V to W is the map is we have a we have to just take a this is like this. So we have a this map is you have a RS is equal to you have a is the form of a V to Z. So RS is equal to this. So you have a again U to V is you have a T, and then V to Z you have a so this is we have a this is U to Z, sorry, this is U to Z. Clearly this is U to Z, and now we have this map is you have a this is U to Z, U to Z you have a RS, and then you have to just say that we can say that W to U to V to W is you have a U to V is you have a T, and this is U V to Z is equal to you have just defined into the form V to Z we define as RS, and this is nothing but is equal to you have a RS over T is again you have a U to Z. So RS over T is again map from U to Z. So both the maps are well defined, and then we can just say that if both the map is well defined, we can clearly say that these satisfy this condition. So therefore this is composition is well defined, and because of both the map is defined, so therefore the composition of a linear transformation is associative. Okay, so this is associative. Now for example, by example we can verify this. We take a R and both we take a R, S and T from R2 to R2 is a linear transformations. R of xy we define into this form, S of this defined into this form, T into defined into this form. So first we have to try to we take R, S and T over xy. This is RS, we have a T of xy. Now RS, T of xy is equal to you have a 2x and 3y, and now we just using the property of this. So we just write in the form of a RS. To just we take this can be written in the form of a R times we have a S of 2x 3y. S T x y is equal to you have a this can be written as R times of a S of 2x comma 0, and this is nothing but is equal to 2x comma 0. R is defined for x plus y comma y, so this is nothing but equal to 2x comma 0. So you can say that RS this is value is nothing but is equal to 2x comma 0. So this means we can say that this way. So other way we have to just say that is again 2x comma 0. So this means we can say that R of Ts is equal to 0, and then we can simply say that this another way, and this is again we just say that this is clearly as then the T of x is equal to 0, Ts xy is equal to 2, then R of Tx. So R of Txy is equal to 0. Now another way we can check is RT and over S. So we have separately calculate RS. So RS is equal to we have x comma 0, R of 0, 0 plus 0, 0. Now we have to operate the T. So T of this is equal to 0, 2x 0, and then we have to show that this satisfy for this is true for all x and y. So this we can say that RTS is the same as a R times T of S. The associative law of a composition of a two linear transformation is satisfied. So composition of a linear transformation is associative, but composition of a linear transformation need not be a commutative. Okay, so now we try to find the composition of some of the examples. Suppose T of defined into this form. We have a V1, V2 and so on, and then S is defined into the this form. So we have a T is defined from, you have a defined from R3 to you have a R4, and this is R4 to you have a R2. So this means we can say that this is, you have a T, this is equal to S. So this is S of T defined from R3 to R2. So this means we can simply say that R3 to R2 is defined. So this is clearly, this is a well defined, because the domain range of this and S is equal to this is a defined. Now we have to try to find the value of this. So S composition T is equal to this. So we can say that S times T of this is V1 plus V2, V1 minus V2, and then we have to just say that. So you have a V1 plus V2, then V1 minus V2 minus V3. So V1 minus V3, and then we have a V2 plus V3, and you have a V3. Okay, so now we have a S nothing but is equal to, we can say that S is the same as we can write here. He is written in the form of a V1 plus V2 plus V3. So we just say that this is V1, this is V2, this is V3. So this rate is a V1 plus V2 plus V1 minus V2 plus minus V3 plus V2 plus V3. And now we have a second term is a V2 minus V3. So V2 V1 minus V2 minus V3, V2 minus V3, V2 minus V3, and then plus V4 plus V3. Now if we simplify this, you have a this is V1, V1, this is equal to 2 times of a V1, V2, V2 is cancel out, then 1 is a V2, and then we have a minus V3 is cancel out, is only here, and now we have to calculate, this is a V1 minus this is V2, and this is V2, so this is V1, so you have a V1 minus 2 times of a V2, and then you have a minus V3. So this is as composition T. We have to just take in the form of a this. Clearly this we have to write into this form. So this is satisfy this condition. So now we have to one more example. We try this define from this V1 plus V2 comma 0, and then as we define as a 2V1 3V1 plus 4 V2. So we have to calculate this ST. So ST we have to calculate it like this. ST can be written in the form of a V1 V2 S times T of V1 V2. Now S times T of V1 V2, we have a V1 plus V2 comma 0, and now this is S is applying is here, so we have to just say that 2 times of a V1, so this is 2 times of a V1 plus V2, and then 3 times of a V1, so V1 plus V2, and we have a plus 4 times of a V2, V2 is equal to 0. So this can be written in the form of a 2V1 2V2 comma 3V1 plus 3V2. This is you have a ST. Now we have to calculate the TS. So we calculate the T of X V1 V2. We have to write. We have a T of S of V1 V2 is T of S is equal to, you have to define the form of a 2V1. So this is equal to 2V1, and next is equal to, you have a 3V1 plus 4 times of a V2. Now we have a, this is nothing but equal to 2V1 plus 3V1 plus 4V2 and comma 0, because V1 plus V2 is comma 0. So this is nothing but is equal to, we can say that 5 times of a V1 plus 4 times of a V2 comma 0. So this is for a TFS we calculating. Now we calculating the value for S square. So S square, we have a x and y, we can write s times s of xy, and this can be written as of x sy is nothing but as we take it some v1 v2, so v1 v2, we have v1 v2, so this is nothing but is equal to s of v1 v2 is equal to 2 times of a v1, 3v1 plus 4 of v2. Now this is again we have writing the 2 times of a v1, so this is nothing but is equal to 2 times of a v1 is equal to 2v1, and now we have a 3 times of a you have a 2v1 plus 4 times of a you have a 3v1 plus 4v2, and this is nothing but is equal to you have a 4 of v1 and 6v1 plus 12v1 plus 16v2, and this is nothing but is equal to 4v1, and you have a 18v1 plus 16v2. This is s square, you have a v1 and v2 is equal to this form. So this means we can say that this is clearly into a this form. Okay, now one more, we have a s t square s, so we can just say that we have a t square s we calculate. So first we calculate the t square v1 v2, we have a t of v1 v2. Now t of v1 v2 is nothing but is equal to you have a v1 plus v2 comma 0, and now this is nothing but is equal to again you have a v1 plus v2 comma 0. So t square is equal to this. Now we have to calculate the t square s of v1 v2 is the form of a t square, you have a s of v1 v2, and now we have a t square s of v1 is equal to 2v1, 3v1 plus 4v2. Then this is nothing but is equal to, this is again you have a 2v1 plus 3v1 plus 4v2 comma 0, and this is nothing but is equal to you have a 5v1 plus 4v2 comma 0. We have a t square of s and v1 v2 is equal to this. So this completes the solution of this all the properties we have to find in there. So this means we can just say that this is equal to you have a like this, all these properties is we have to calculating here. So I just say that I just try to one more last example for this session. We show that s of t is equal to 0, but t of s is need not be equal to 0. So we have a two composition map is there, st and ts. We already show that this is equal to 0. So we find an example where st is equal to 0, but ts is not equal to 0, non-zero example. So s and t are the two linear transformation defined by this. S is clearly the non-zero, t is also clearly the non-zero. And now if you calculate the s of t of x and y is equal to s times t of xy, then s of t of xy is equal to your x comma 0. And now by the definition of this s, we can, this is 0 comma y is 0 and comma 0. So this means clearly s of t is so we can say that s of t of xy is equal to 0 0. So this means s of t is clearly equal to 0. Now we can calculate the t of s of you have a x and y as a t of s of x and y, and this can be written as t of s of xy is equal to you have a y comma 0, and now this is nothing but is equal to this is again you have a y comma 0. So this clearly t of s is equal to 0, but t of s of t is equal to 0, but t of s is not equal to 0. We have to just prove that. So this st is equal to 0, but t of s is not equal to 0. So this complete where we have to find two non-zero linear transformations where composition t composition s is equal to 0 and t s composition t is equal to 0, but t composition s need not be equal to 0. We have to just say that. Okay, one more example we have to calculate for the case of a polynomials. So this is we define into this form. So we have to try to find what is st and ts. So st means simply we calculate the form of this. So we have to first calculate st. We have a polynomials of p2. So st on the polynomials of you have a in the form of we take as something like is equal to a naught plus a1x plus a2x square, and then we can write this is s times you have a t of a naught a1x a2x square by the map of t. T is map is equal to this. We have a 2 times of a ax. So this is a constant is here. The 2 times of a into x plus the coefficient of a x. So we just say that 2 times of this is equal to 2 times of a2 x plus coefficient of this is equal to a1. Now s is defined in the form of we have a 2 times of a of the 2 times of the coefficient a x square, the coefficient of x square, and this is the 2 times of this plus coefficient of a b into coefficient of x. So this can be written as 2 times of a this is here we have to coefficient of this x square. So in this case we have to just say that we have a x square is not involving here. So this means we can say that x square is not involving here. So what is we have to left only? We have to check is the this term is equal to we have a 0 because the coefficient of x square is equal to a is equal to 0. So this is 0 plus we can just write in the form of a 0 plus we have a b of x coefficient of a b with the coefficient of x is equal to this is a twice a2, and we have to just say that is equal to x. So this is equal to twice a2x. This is st. Now we calculate the t of s. We have a naught a1x a2x square is equal to t times of s of a naught a1x a2x square t times of a twice a2x square plus a1x. Now operating the t is saying that what is the coefficient of x square and 2 times the coefficient of x square is equal to this. So you have 2 times of a twice a2 into x plus coefficient of this a1 is equal to b. So this is equal to 4 times of a2x plus a1. This is you have a t of s is into defined is a naught a1x plus a2x square. So in this case we have to define both the maps in this way. So st and ts is equal to in this form. So this means in this class we discuss about the composition of a two linear transformation is again is a linear, and we discuss some examples and calculate how to calculate the composition of a two maps. And we also show that the composition of a two linear transformation need not be commutative, but composition of a two linear transformation is a associative. So now I stop today's class in this point. In the next class we continue some properties of the composition of a this linear transformation. Thank you very much.